Welcome to Module 1 of Electronic Circuit Design. In this module, we will focus on the fundamental building blocks of analog circuits, transistors, amplifiers, and feedback systems. We will begin with the operation of transistors at low and high frequencies, then move to multistage and feedback amplifiers, followed by stability concepts, oscillators, signal generators, and wave-shaping circuits. 1.1 The transistor at low frequencies. At the heart of modern electronic circuits lies the transistor. At low frequencies, transistors can be treated as nearly ideal devices. In this regime, the focus is on how to bias the transistor correctly to ensure stable operation. Biasing means setting up a fixed operating point so that the transistor functions in its active region. If the bias point is too low, the transistor may cut off, producing distortion. If it is too high, the transistor may saturate, again limiting performance. Proper biasing ensures the transistor can amplify signals without distortion across the expected input range. Several biasing techniques are used in design, including fixed bias, voltage divider bias, and current source biasing. Each method has trade-offs between simplicity, stability, and sensitivity to component variations. 1.2 The transistor at high frequencies. As frequency increases, transistor behavior becomes more complex. At high frequencies, internal capacitances within the device cannot be ignored. These capacitances slow down the response, limiting the transistor's ability to amplify signals at very high speeds. Key points to consider at high frequencies. The transition frequency defines the maximum frequency where a transistor can provide significant gain. Parasitic capacitances, such as between base and collector, introduce phase shift and reduce gain. Designers often use special transistor geometries or compensation networks to extend frequency response. Understanding high-frequency transistor behavior is essential for radio frequency amplifiers, communication circuits, and high-speed digital electronics. 1.3 Multistage amplifiers. Often, one amplifier stage does not provide enough gain or signal conditioning. In such cases, multiple amplifier stages are cascaded. The first stage might be optimized for input impedance, ensuring minimal signal loss. Intermediate stages provide voltage gain. The final stage provides power gain, driving the load effectively. When designing multistage amplifiers, careful attention must be paid to coupling between stages, impedance matching, and the cumulative effect on bandwidth and distortion. 1.4 Feedback amplifiers, analysis and design. Feedback is a cornerstone of electronic circuit design. By feeding a portion of the output signal back to the input, designers can control gain, reduce distortion, and stabilize performance. There are two primary types of feedback. Negative feedback, where the feedback signal opposes the input, stabilizing the amplifier and improving linearity. Positive feedback, where the feedback reinforces the input, a principle that leads directly to oscillators. Feedback amplifiers are analyzed by considering how feedback changes gain, input and output impedances, and frequency response. Design involves balancing stability with the desired performance improvements. 1.5 Stability concepts and oscillators. While feedback brings many benefits, it can also lead to instability. If the loop gain and phase shift of a feedback amplifier are not carefully managed, the circuit may oscillate unintentionally. Stability analysis involves determining the conditions under which oscillations might occur. Designers use concepts such as phase margin and gain margin to ensure robust stability. When intentional oscillations are desired, feedback is harnessed constructively. This is the principle behind oscillators, which generate periodic signals without requiring an input. Types of oscillators include RC oscillators, suitable for audio frequencies. LC oscillators, used for radio frequency applications. Crystal oscillators, providing extremely stable frequency references. 1.6 Signal generators and wave-shaping circuits. Signal generators provide test signals for measurement and design purposes. They can produce sine waves, square waves, and triangular waves. Wave shaping circuits further modify these signals. Clipping circuits remove portions of a waveform, limiting amplitude. Clamping circuits shift the waveform up or down without altering shape. Rectifiers convert alternating signals into unidirectional ones. Such circuits are crucial in analog processing, communications, and power supplies. In Module 1, we examine transistors at both low and high frequencies, explored biasing techniques, studied multistage and feedback amplifiers, analyzed stability, and introduced oscillators, signal generators, and wave shaping circuits. These are the fundamental blocks that allow electronic circuits to amplify, shape, and generate signals. In Module 2, we will move to more advanced design-oriented topics, including power amplifiers, operational amplifier applications, distortion analysis, variable gain amplifiers, and automatic gain control systems.